All right, welcome to the review for Chapter 6, Quadratic Functions. Before we start, remember to gather all of your tools every time you do math. What you need to have is you need to have a pencil. I don't have a pencil right now because pencils don't show up all that well on my screen, but I do have an erasable pen just in case I make a mistake. You also need your calculator. You also need the actual thing that you're working on. So there's all three of my tools. What's the first step whenever you take a test or do homework? Put your name on it so that whoever's grading it knows to give you credit. So let's take a look. Number 1. So here's a pattern of squares. Use it to help you with questions 1 through 3. So figure 1, we got some weird looking C shape. Figure 2, a weirder looking C shape. Figure 3, same shape, just bigger. So let's see, draw the figure 4 in the picture. So because we're working on quadratics, quadratics are based on the idea of something is squared. Squared means I'm looking for squares. So I see a 2 by 2 square, a 3 by 3 square, and a 4 by 4 square with a bunch of other stuff happening. So figure 4 must be a 5 by 5 square as the square base. And remember, this is math class, not art class. So if your squares are not all exactly the same size, nobody's going to take points off of it as long as you have the same general pattern. All right, it also looks like our bottom row always extends 2 beyond whatever our last thing was. So we're going to add another 2 down at the bottom. And the top row also extends 2 beyond, but it doesn't always go all the way to the left end. So I'm just going to start here and end that with my 2 extras. And that is number 1. Explain how you see the pattern growing. Well, I kind of did that a little bit in my mouth words, but now I got to do it in my hand words. I see a big square in the middle with each side growing by 1 in each step. I also see that both the top and bottom rows go 2 blocks farther right than the square. But the top row has 1 block less on the left. Something like that. Now, which of these expressions, which of these 4 equations could actually make S, or could actually tell us what to find, or how many blocks are in each figure based on the figure number? So I'm kind of going to look at figure 3, where 3 is going to be my input, and 4 by 4 means I've got 16 blocks here, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So anything that I can plug in 3 for my N and get 27 as an answer is going to define my S. So let's look at this. If I have parentheses 3 plus 3 squared minus parentheses 3 plus 1 squared, I get 20, which is not 27, so A is out. I'll try the 3 plus 1 squared plus 3 plus 2 plus 3 plus 3, and there we go. And I get 27 for that one, so that one's a maybe. try C and D just in case there are multiple answers. If I have 3 squared plus 2 times 3 plus 4, that's 19, which is not 27. And if I have 3 squared plus 4 times 3 minus 4, that's also not 27. So B must be the answer. Now, you could also have kind of gotten that by looking at, well, figure 1 has a 2 by 2 square. Figure 2 has a 3 by 3 square. Figure 3 has a 4 by 4 square. Figure 4 is going to have a 5 by 5. The square part is the number plus 1 squared. The top part is the number of squares you have plus 2 more. And the bottom part is the number of squares you have plus 3 more. So that's another way of getting that, however you want to get through that. Number 4, which of these tables could represent a quadratic function? Use a full sentence to explain how you know. So with quadratics, we want to look for a couple of different things. We want to look for numbers getting bigger than smaller or getting smaller than bigger. So 144 to 36, that's getting smaller. 36 to 0, that's smaller. 0 to negative 16, smaller. Negative 64, still smaller. So that one can't really be a quadratic unless they're trying to trick you, which we're not. Negative 100 to negative 10, that looks like it's times 10. Negative 10 to negative 1, that looks like it's times 10. Negative 1 to 10, that's not times 10, but it is getting bigger and bigger and bigger and bigger as we go. So that's probably not a quadratic either. But if I go 1 to 4, that's going up. 4 to 5, that's going up. 5 to 4 is going down, and 4 to 1 is going down. If you see that nice mirroring, that is definitely a quadratic. So table C represents a quadratic equation because the numbers get bigger than smaller. The y values. At some point in the future, we will tell you guys about finite differences and second differences. All right, continuing on. Number 5. A water balloon is shot up into the air with a catapult. The function h given by h of t equals 10 plus 45t minus 16t squared models the water balloon's height in feet t seconds after it was launched. So again, anytime we're talking about height and saying t, that looks like our physics equation, which can be h of t equals at squared plus vt plus h0. Again, we could call it v0. Now, they kind of switched the position on these, but that's okay. The domain of this function only contains values greater than or equal to 0. Yeah, because anytime we're talking in the real world, you start counting at 0 and move forward. You know, we don't necessarily deal with what happened to the rocket 3 weeks before we built it. We're not going to deal with negative time that way, so that is true. The water balloon is at the same height 2.8 seconds after launch as when it was launched. Well, when it was launched, it was at 10 feet. And 2.8, that looks like it might be true. I'm not sure exactly because they didn't really give me decimals here, but I'm going to say that's true. The balloon reaches the ground at 3 seconds. That looks like it's true to me. The balloon is 15 feet above the ground when it's launched. Now I can see right there that it's at 10, so that's false. And the value t equals 2 does not belong to the domain, but 2 is bigger than 0 and smaller than the 3 where we landed. So that is, that one's false. Now there's a little tiny logical thing that makes this one false and this one a little bit more true. Technically, our domain goes between 0 and 3, because we launch at 0 seconds, we land at 3 seconds, and why are you still running the clock after that? However, they're really asking about only values greater than or equal to 0. They're asking, can we make negative numbers? And the answer is no. All right, what do each of the things mean? Negative 16 or negative 4.9 means gravity. That's your A, your acceleration due to gravity. The 10 is your h sub 0, your starting height, your y-intercept, all those same thing. That's your starting height. And then the 45, the middle number, that is your starting speed. And speed, technically, it's actually your velocity. What makes it velocity is having either a positive or a negative telling you what direction it goes in. All right, number 7. Parts of a graph. The axis of symmetry always goes straight up and down through the vertex, through the highest or lowest point. So this is your axis of symmetry right here. The y-intercept is where we cross the y-axis. There's your y-intercept. The x-intercepts are we cross the x-axis. So there are your two x-intercepts. And the vertex is either the highest or lowest point that goes through the axis of symmetry. That is your vertex right there at the bottom. Okay, next page. And I'm going to stop recording this partway through this class and then stitch 2 videos together at the end of the day, I think is what I'm going to do. Number 8, identify the error in the following student's work and explain how to fix it. X plus 2 times negative x minus 5. Okay, negative x minus 5 and x plus 2. X times negative x is negative x squared. That's fine. Negative x times 2 is negative 2x. X times negative 5 is negative 5x. And negative 5 times 2 is negative 10, so that's okay. But it looks like they added wrong. So 5 minus 2 would be 3, but negative 5 minus 2, they should combine the middle term differently. So combine negative 2x and negative 5x to make negative 7x instead. So that means that their correct answer should have been negative x squared minus 7x minus 10. Ooh, so they messed up twice. So let's also go back. They also made the 10 positive. And here, and switch the 10 to a negative. And there we go. Number 9, convert this from factored form to standard form. We have a few different ways of looking at that. We can use the area method if we want. So we have x minus 7 times x minus 5. X times x is x squared. X times negative 7 is negative 7x. X times negative 5 is negative 5x. And negative 5 times negative 7 is positive 35. When we add our negative 5x and negative 7x together, we get negative 12x. So y equals x squared minus 12x plus 35. One of many ways of getting through that. Number 10, graph this quadratic equation. Make sure to include the vertex, x-intercepts, and y-intercepts, and at least 7 points. So it looks like my x-intercepts from the intercept form or factored form are going to be at, remember, anything inside parentheses with your x is lying about its sign. So this minus 5 should actually be a positive 5 comma 0. This minus 1 should be a positive 1 comma 0. So your x-intercepts are positive 1 comma 0 and positive 5 comma 0. We also know that our y-intercept is at 0 comma 5. Our axis of symmetry is going to be halfway between our two x-intercepts, so let's put that in here. We can also calculate it if we have to by taking negative b divided by 2a from the standard form. It looks like our b value is already negative, so we have negative negative 6 over 2 times 1. Negative negative 6 is 6 divided by 2 is 3, which is exactly where it looks like it should be. In order to find the y value of the vertex, we need to plug in any one more point. We need to plug this into either equation. I'm going to pick the intercept form. So y equals 3 minus 5 times 3 minus 1, or negative 2 times 2, which would be negative 4. So my vertex is at 3 comma negative 4 right there. And we've already got 4 points. We can also get a mirror point if we are 1, 2, 3 to the left of this line. We also need 1, 1, 2, 3 to the right of this line. Honestly, for me, for my class, I'm okay with 5 points. They want 7, so let's pick another number. Let's plug in 2 for x. So if y equals 2 minus 5 times 2 minus 1, 2 minus 5 is negative 3. 2 minus 1 is 1. Negative 3 times 1 is negative 3. So 2 comma negative 3, that's 1 block to the left. That means I should also have 1 block to the right. And my equation, my curve, will look something kind of like that. All right, I'm going to pause there because we're about to run out of class time, and it'll take a while for this half of the video to compress. Welcome back. We are still working on the Chapter 6 practice test on quadratic functions. Again, as before, whenever you're working on a test or any sort of math, you want to make sure that you have all your tools before you start. Tools that you need, you definitely need the actual questions that you're working on. You probably want a calculator, and you need a pencil. I don't have a pencil because, again, pencils don't show up very well in the video, but that's okay. I have an erasable pen, so that'll help out. So just in case I mess something up, I can get rid of it. Cool, huh? So we got through number 10 in the first half. We're going to go start with number 11 here. Find the vertex of this equation. Y equals 3x squared minus 12x plus 9. That looks like the standard form to me, where y equals ax squared plus bx plus c. And the vertex has to go through the axis of symmetry. The axis of symmetry formula is where x equals negative b divided by 2a. So my b value looks like it's already negative 12. Looks like my a value is positive 3. So we are looking at negative 12 divided by 3. Well, negative 12 is really just 12, and 12 divided by 3 is 4. So my vertex is going to be at 4 comma something else. In order to find the y value of the vertex, you just need to take that x value, plug it right in. So if y equals 3 times x squared, but x is 4 squared, minus 12 times x, or 12 times 4, plus 9, we could go through this step by step if we want, but this is also why we've got a calculator. 3 times 4 squared minus 12 times 4 plus 9 is 9. So our vertex is at the point 4 comma 9. And there we go. Number 12. 12 through 15 are about a company selling cell phones. Mimi discovers that her scores on her weekly... I bet the real test is going to talk about selling cell phones instead of test scores. Mimi discovers that the scores on her weekly math quizzes are a function of how many minutes she spends studying. The function f of x equals 0.2x times 150 minus x models this function. And again, this does actually sound like it makes sense, because if you study, oftentimes your grade goes up. If you stay up way too late, spending a lot of worry energy about studying more and studying more and studying more, oftentimes you stress yourself out and do less well. So this actually does happen where, if you study for 100 hours, you probably actually overstudied, and you might end up, tiring yourself out and not doing as well as you wanted, as opposed to if you only studied for 60 hours, you might get a higher score, or whatever. So what are the x-intercepts of this function? We have a couple of different ways of finding them. First off, we could take the function model that we've got right now, f of x equals 0.2x times 150 minus x. That looks like the intercept form equation where y equals x minus p times x minus q. And the p and the q tell us exactly where the intercepts are. So if 0.2x doesn't have anything adding or subtracting, it means that our p value must be 0. And the y value of every x-intercept is always 0. We can also see 0, 0 as an x-intercept on the graph. And if we have 150 minus x, then in order to make that switch around and go away, then the the x value must be positive 150 comma 0. Again, it might be a little bit easier to see on the graph way out here where they tell us that's where x is 150 and y is 0. Might be a little bit easier that way. What do the x-intercepts represent? They represent the amount of studying that would get you a 0%. If you study not at all, you get a 0%. If you study for 150 minutes, probably 150 hours. Then you've overstressed yourself. You came in, you were too tired, you fell asleep during the test, and you got a 0 as well. So which of these equations could also be r of x equals 0.2x times 150 minus x? Select all that apply. So let's see here. If I distribute where r of x equals 0.2x times 150 minus x, then I'm going to have a 0.2x times 150, and I'm going to have a minus because of the negative sign here, and I'm going to have my 0.2x times the other x. So do I see that anywhere in here? That looks like the fourth choice. So again, some of these might be a step in your work rather than your final answer. So if I take my 0.2x times 150, 0.2 times 150 is 30. X minus 0.2x times x is 0.2x squared. And that means that r of x equals 0.2x times 150 minus 0.2x times x is our only number, or our only thing that works. The top one looked like it was going to work, but it said 3x instead of 30x. And, again, just double checking, 0.2 times 150, yeah, that's still 30. So, fourth one is the only one that's going to work for us. And looking at number 15 here. Mimi thinks that she should only study for 75 minutes because that seems to be the amount of time that results in her highest quiz scores. Mimi's mom wants her to study for 90 minutes because more studying is always better. Who's right? Well, let's see here. According to the graph, if Mimi says she studies for 75 minutes, well, way up here at our vertex, that's where we get our 75, 99. Here, let me pull that down so we can see that. But Mimi's mom wants her to study for 90 minutes. 90 minutes looks like that's probably only a 95. That's where she's started to tire herself out a little bit. So it looks like in this case, Mimi is correct and her mom is wrong. So Mimi is right because the vertex of the graph shows that at 75 minutes studying, she scores 99%. But if she studied for 90 minutes, she only scores 95%. Her mom's suggestion would get her a lower score. And that's number 15. And again, for my live studio audience, I know that I am going through too quickly for you guys to capture everything. That's why I'm recording it, so that we can put it up on YouTube in a second. And you can pause it whenever you need. All right. Rudd and Lauren were at the park with some friends. Rudd threw a ball up in the air as high as he could. This graph represents the height of the ball t seconds after it was tossed up by Rudd. Okay. What is the domain of this graph? Please explain why you picked that domain. So again, in the real world, we only start counting things when they start happening. And we stop counting things after they finish. So from the moment the ball leaves Rudd's hand to the moment that it lands on the ground would be from 0 seconds, where it is launched, to that looks like probably about 4.2 seconds, something like that. Again, if they don't give you good tick marks on that, just eyeball it and make your best guess. So the domain of this graph is where we have a few ways of writing this. We could say that x exists between 0 and 4.2 seconds. We could say that x is between 0 and 4.2 seconds. There are a few different ways to say that. And I know this because the ball was thrown at 0 seconds and it landed at 4.2 seconds. And there we go. Number 17. Lauren wanted to see if she could throw the ball higher than Rudd. So we still have the graph of Rudd's throw here on the left. And now we have an equation that represents Lauren's throw. So here's Rudd's throw, here's Lauren's throw. For Lauren, the function f of t equals negative 32 times x minus 0.9 squared plus 30 represents the height of the ball t seconds after it was thrown by Lauren. So it looks like that's Rudd is me. Sorry about that. Rudd's stone reach a maximum height of, looks like at about 2 seconds, we got to a height of 24 or 25, somewhere around there. Let's call that 2, 25. So 25 feet. And Lauren's, we need to figure out, based on the equation, it looks like she's got a vertex form. Vertex form is where y equals a times x minus h squared plus k. So it looks like if the minus h is minus 0.9, h is 0.9, and the k value is 30. So the vertex on her equation is at the point 0.9, 30, which means that its maximum height is 30 feet. So it looks like Lauren threw the stone higher than Rudd did. which means that Lauren threw it higher. And number 18. Another way to look at Lauren's equation is where f of t equals negative 32 times t minus 1.87 times t plus 0.7. So that would be the intercept form. Dylan says that Rudd's ball was in the air longer than Lauren's. Do we agree or do we not? Well, let's see here. From the domain and from the graph, we already saw that Rudd's ball landed at about 4.2 seconds. If we look at the factored or intercept form, where y equals a times t minus p times t minus q. Again, I use t here since that's what they did. You could use an x if you want. Looks like the p value is 1.87 seconds, and the q value, if we switch the sign, is negative 0.7 seconds. So it looks like Lauren's ball landed, or rock, or whatever she threw, landed at 1.87 seconds. And if Rudd had his rock land at 4.2, but Lauren had hers land at 1.87, that means that Rudd actually spent more, or his rock or ball or whatever was thrown, spent more time in the air than Lauren. So I agree with Dylan. That was for number 18. All right. So again, I agree with Dylan because Rudd's ball landed later, after about 4.2 seconds. Lauren's ball, however, only flew for about half of that, 1.87 seconds. So 4 seconds versus 2 seconds. Lauren's must not have been in the air for quite as long. And that is the end